The nice thing about EEG and MEGR is that they have very high temporal resolution, which also means that we can analyze data in the frequency domain, not just in the time domain. It's been known for quite a while that different frequency ranges in the ongoing EEG seem to reflect different brain states, like different levels of alertness, drowsiness, or in sleep, for example, different sleep stages are characterized, partly at least, by different signals at different frequency ranges. Also, if you look at the topographies of these signals here in the EEG at different frequencies, you will see that they differ, at least between certain frequency ranges, suggesting that the neural generators are different, or the distribution of neural generators are different, and therefore the different frequency ranges reflect signals from different brain regions, different brain networks potentially. So you can see that here, at least between the very low frequencies and the alpha range, alpha and beta range, this looks different, and then the gamma range looks different. And you can look at these between signals and compare them between different participant groups, tasks, stimuli, and so on and so forth. And obviously, there are loads of studies that have done that. And in order to understand what the analyses that have been done in these studies, and if you want to do this yourself, I think we have to do a little bit of go through some basics in order to be at the same page, to look at the at frequency and time frequency decompositions. But these analyses are the basis for some approach that's based on brain rhythms or oscillations. And there are quite a few authors, obviously, who have proposed ideas on this subject, but this is just one example here. So, I mean, we all often look at univariate differences here between brain activation, and we may find differences between different brain regions, between conditions, tasks, participant groups. But of course, it's also possible that there are certain networks that communicate, or certain brain areas that communicate in certain frequency ranges. This is indicated by different colors here. So, and if we are lucky, then these different networks that activate in different frequency ranges also reflect different processes here, 1, 2, 3. And they can potentially be interpreted as different canonical computations. So that would be the ideal world, of course. Different frequencies reflect different networks that reflect different computations. And that means simple frequency analysis may already provide us with the building blocks of our cognitive model of our choice. But yeah, back to basics here. So I would really like to start at the very beginning before we can talk about more interesting things. So the basis of these analysis methods is usually that one can decompose any signal into basis functions that reflect periodic signals. And that's most of the time, those are sine and cosine functions. So they are periodic with a certain period t. Sine and cosines basically have the same shape. They're just shifted in time. They have a certain phase difference. So that means at every frequency, you can actually have two orthogonal functions like that describe a signal at this frequency. And we will use that a little bit later. By definition, a periodic signal repeats itself with a period t. I mean, that's a time period. Not exactly rocket science. I mean, one way to describe signals like that is the sine curve, or the cosine function. And in order to describe these periodic signals, well, you have time that just relentlessly moves forward. You have a frequency that determines, how quickly your sine curve goes up and down over time, or in a certain time period. I mean, this 2 pi in this case is, if you like, a scaling factor. It reflects the circumference of a unit circle. That means every time the frequency increases by an integer, you have an additional period within a certain time period. You've done it, yeah. So obviously, if you have the number 1 here, then and you move on by 1 second, then you go around the circle once. If the frequency is 2, then within 1 second you will have gone around the circle twice. So that is how this bit of the equation is explained. And you also have a phase here in this equation So if your signal gets shifted forward or backward in time, just like we just actually saw on the previous slide. So sine and cosine are basically just differ with respect to a phase difference. One is ahead of the other, or the other way around. One is behind the other. This is reflected in a phase difference, often indicated as theta here. And I already indicated that this kind of signal can be described by the movement of a pointer around a unit circle. So just imagine this black pointer here moves around. You have 2 pi, that's in radians, that's the circumference of a unit circle. And you look at the length of the y coordinate here along the unit circle, then this movement would describe a sine curve. If you start here and then you start moving with a constant speed, and the speed is related to the frequency. And if you then scale that with this 2 pi here, and this explains this part of the expression here in the formula. And if you jump ahead or behind, then this would be reflected in a phase difference. And this is, for example, important if you have more than one signal. So you can, in principle, have a signal, 2 signals at the same frequency, but at different phases. Or the phase of one particular signal can change over time. So that is something for maybe a later session. This is a little bit more complicated by the fact that you can measure the angle or the position of this pointer here in different ways. I mean, I started by using the most common way, at least in the engineering literature, the data analysis literature, using the units in radians. So the unit circle has the circumference of 2 pi. Often, I mean, we start learning about these things in terms of degrees. So one round around the unit circle can also be described as 360 degrees. So in terms of the angle here that this pointer has with respect to the x-axis. So this is just to avoid confusion in case different papers maybe use different units, but I think the most common one is the one in radians here. Yeah, and this is a correspondence I already mentioned. So if you go around the circle once, then you've covered 2 pi on the unit circle or 360 degrees here. And well, we can actually look at that. I mean, it's, well, wait a second, where is this? It's a bit strange, of course, to look at a YouTube video within a YouTube video, but I'm doing it anyway. So if I start that, I mean, here you have your pointer on a unit circle. And if you look at the y coordinate here, then it describes a sine curve. If you look at the x coordinate here, it describes a cosine curve. In principle, these are the same, just shifted in time. And you can plot them both together here. And I mean, this, I think, illustrates nicely how the periodic signal can be conceptualized as resulting from this periodic movement, or this movement of a pointer around a unit circle with constant speed. And the speed corresponds to the frequency. And later, I mean, if we have signals that are not on the unit circle, then the length of this pointer here would correspond to the amplitude of the signal, and the angle with respect to the x-axis that corresponds to the phase of the signal. Okay, that's nice. So what can we actually do with it, or how do we usually deal with it? There is something else that we need to talk about. I mean, if you read some papers, you will usually see these things described not with sine and cosine functions, but actually with complex numbers. I mean, they are called complex not because they are very, very, very complex. In fact, they actually make things simpler in terms of notation. But I mean, complex numbers are called complex because they have the strange idea of the square root of -1 in it. I mean, this is not really important here. It's really just a name. It's just terminology. And I once opened a textbook, Mathematics for Biologists, where I was hoping to find a nice introduction to this topic. I mean, also for people who are maybe new to this topic, who are starting with data analysis. And in the introduction, it said, oh, well, we are not dealing with complex numbers in this book because people rarely need them. However, quite a few textbooks or papers, introductory papers on this topic for time frequency analyses or even just frequency analysis in EEG and MEG actually use these complex numbers. So I thought I should just explain them a little bit. It's all based on something that's called Euler's formula. So this movement of this pointer around a unit circle. So is described by the x and the y coordinate of this point. And these two, I mean, this coordinate is basically captured by both the cosine and the sine part are captured by this kind of simple formula here involving Euler's number, and then to the power of minus I, that's the complex number I, and the phase of the signal. So this is the relationship here that was discovered by Euler. It's also the guy who I think lived in Königsberg and discovered, that you know how to cross the 7 bridges there. Yes, so and this is quite a fundamental equation. But I think we only need to remember that it's a more convenient way to capture this trajectory of this point on the unit circle, which keeps track of both the sine and the cosine part and the phase with respect to the x-axis here. It's basically a way to collapse these two different types of information into one simple number. This is the mathematical identity here, but that means that we can describe a signal in this domain, in terms of the pointer on the unit circle with this compact formula. So not explicitly mentioning a sine and a cosine. So in this case, by using the complex number, we have at our disposal the real part and the imaginary part of the complex number. So that is sort of hidden within this formula here. We can add an amplitude here. So that is the amplitude of the signal, which potentially which is reflected in the length of this pointer here if it's not on the unit circle. And apart from that, there's the time domain. So time just moves forward. We have the frequency, and we have here the circumference of the unit circle. And why are we going through all this trouble? I mean, it's not just an easier way to describe a periodic signal. It's actually also a better way of describing relationships between different signals. So if you have two signals here that both move at the same frequency around a circle here with different amplitudes in this case, and you want to compute things like the cross spectrum, so you want to see how these signals are related in this frequency and how consistent they are with respect across trials, for example, or across a continuous data set, then you can do that by multiplying these signals in a certain way. So complex numbers offer you a certain kind of I would say compact mathematics to establish relationships between these signals. So in the end, if you have these two signals described by their amplitude and by their description in the polar representation, so that's basically what it's called here, then you can just multiply them in this polar representation, and you can easily establish relationship between the signals. The amplitudes in this case just multiply, and the phases, basically you get the difference of the phases of these signals. So long story short, and I don't know if I really made things very clear here, these complex numbers are a convenient way to describe periodic signals and their relationships to each other. Unfortunately, even if you look at the tutorial, so Bastos and Schöfferlin, it's a nice paper that I really recommend. I actually got this figure from this paper, but even though it's a tutorial and it's trying to introduce people to the subject, they quite quickly arrive at complex numbers and present you with these formula. So if you want to at least have some idea of what these formulas mean in different papers, then you should maybe meditate a little bit over this polar representation and these visualizations here. But apart from that, I think you don't necessarily need these details. You don't have to study these details in very much depth, and we can in other sessions move on to the Fourier analysis and then to the time frequency decomposition of signals.